All right. Hello, everyone. Welcome to the third class of the Intro to Physics here at Simple Tutor. First thing we're going to do today is just quickly go over the homework from last class. Kept it pretty short, pretty easy for you guys. The first question was, what are three Newton's laws that we discussed? I'll answer this one myself because I'm pretty sure all of you guys know it. F equals ma. Every action has an equal and opposite reaction, and then the law of inertia, which is an object stays in rest or remains in motion until acted upon by some kind of external force. And then I gave you these three scenarios. One is a box on a flat surface, one is a box on sort of an inclined plane, and then one is just like a ball or some kind of object that is sort of just dropping and free falling. So I'm gonna ask a couple of you guys to sort of tell me like how exactly would you draw this free body for each one? So for number one, can I get it? Okay. Yeah, Schmidt, you raise your hand first. Can you tell me how you would draw this free body?
So for the free body, I put a arrow pointing down with the box, and that one was gravity. And then I also did an arrow pointing up, which was the normal force.
Yep. Okay. Pretty easy. We have the gravity force pointing down and the normal force pointing up. For the second one, Ishan, can you tell me what you did for this one?
Gravity's pointing down, and the normal force is pointing like away from the inclined plane, basically.
Yeah. The best way to sort of describe that is sort of like perpendicular to the plane. But yeah, that's it. So you have your gravity going down, and then you have sort of your normal force coming from the surface at the angle. And our last one, can someone raise their hand and tell me how do we do this one? How do we draw this free body? Okay, yeah, Ishan again, you can go.
Just gravity pointing down.
Yeah. This one is easier than all the other ones. We only have one force. It's just gravity. There's no surface, so there's no normal force. So pretty easy. Let me switch my share. Okay, here we go. So today, now that we know our basic Newton's laws that we're going to use for physics, and we know how to draw a basic free body diagram, I want to get into a little bit more components of free body diagrams and application of Newton's laws in actual problems, pretty basic problems. I'm not going to make it too difficult. And also, I sort of want to, if we have time, I'm thinking we can get into sort of a little bit of what we call kinematics. I'll explain more what that is because a lot of you guys probably do not know. But for now, let's get into what I know we're going to do. So we're going to start off with some more, I'd say, advanced concepts in terms of free bodies. So let's draw this inclined plane, for example, again. And we have this block, right? And as we went over in the homework, as we went over last class, our free body, obviously I'll draw this out, but these are our two forces. So our free body would look like this is our basic free body. And if some kind of test you had and they asked you to draw the free body, this is how you would draw it. But as you can see, we can't exactly set up an equation for this. And what exactly do I mean by that? Well, in last class, we also talked about this, is when we had a box flat on an incline, we were able to set up an equation between our two forces, right? We were able to set up the equation that Fg equals Fn. Why? Because the box is not moving and both forces act in the exact same plane, right? So another way, of course, you can write this as mg equals n. But now we have a much different scenario because we can equate something that's pointing directly down with something that's pointed at a little bit of an angle, right? This force is a little bit of an angle. So that's where our components come in. So for the purposes of actually drawing the free body, we don't need to know our components. But when we need to set up equations in regards to the free body, based on the free body, is when we need to start focusing on components. So typically in these scenarios, right? This is the most common physics scenario where you really need to draw components. The way we do it is we sort of break up this force, this gravity force, into two components. We'll have sort of a vertical component, right? The reason I'm drawing it with these lines right here is just to sort of show that they're components and not new forces. And you'll have sort of a horizontal component. And sort of really the best way to think about this is that this is sort of the addition of this vector and this vector. And this might be complicated. Most of you guys probably don't know what vectors are, but really when we have sort of an incline or like an angle between our forces, we're going to start to draw these components to balance out and create these new equations. So and of course you're going to need to know trig. So when it comes to the time when you guys actually do these problems, like in class or in a real course, you will need to know trig. You will need to sort of understand how to break these components up, and this is really the best way. So sort of we need to sort of match the plane of the forces. So because I don't want to make it too advanced, I don't want to actually get into the trig because many of you guys probably do not know. That's totally fine. But this is just sort of something really important to remember. Because when we really need to set up our equations, and really in physics, it's really important to remember that when we have questions that ask us to draw free body diagrams, because sometimes they won't, because usually it's considered free points, because it's pretty basic, right? When they ask us to draw free bodies, we're going to need to know how to set up an equation based on those free bodies in some way. It'll ask for some quantity, and we're going to need to set up some kind of equation, right? So it's important to remember how to split up your sort of forces and create these different components based on the X and Y dimensions. But for the math wise, I don't want to get into it. But okay, now I'm gonna give you guys a slightly different scenario. And I want someone to tell me how you would break these up into components. Okay. So let's see. Okay, we'll just have sort of a plane in the opposite direction, right? So we have this block right here. And it is sliding down this ramp. There are no other external forces, but the force of gravity and the force of the normal force. So therefore, our simple free body diagram would be based on these two forces, right? This is not really an arrow. This is just try to show the direction of the movement. But this is what our free body diagram is sort of based on. Simply, it would be something like this. Now, can someone unmute or raise their hand and tell me how would I split up one of these forces into components? So first off, which one, right? So this is our normal force, and this, sorry, my bad. This is our gravity, and this is our normal force. So tell me, actually, I want one of you guys just to unmute and tell me which force would I break up into components? And I want someone else after that to tell me how would I break them up? So someone can raise their hand and mute, just let me know. And if no one knows, I'll do it myself. But if someone could sort of at least try, it would help sort of me understand where you guys are at with this.
I don't know how to do it because I don't understand why you split up the things for the
Okay.
other.
Okay. So you don't understand why we split it up? Again,
First
all right.
example.
Okay. That's a good question. Well, and as I said, for the purposes of actually drawing the free body, we do not split it up. So when we think of our components, they're really only there to help us create our equations and sort of find certain variables. As I said, because these two forces are not pointed in the exact same plane or direction, or therefore we can't really create an equality between these two
I get it now.
quantities, right? Yeah, exactly. So that caused us to break up our forces into components, and that'll help us sort of create exact and equal equations.
So would you split up gravity?
Yes. Yes. That's right. Typically, as I said, we're going to be splitting up the gravity force because, well, it's directly pointed down, so it's a vertical force, right? So therefore, it allows us to break it up based on this right angle. I know that might be confusing. You're going to need to know a basic trick to sort of understand why we're breaking up gravity and not the normal force. But just for the purposes of this class, remember that we are in these inclined plane scenarios and declined plane, like really, we're going to be breaking up gravity because gravity is always pointed down no matter the scenario. So, can someone tell me how would I break these forces up?
You would have the velocity, and then gravity, and the normal force.
Okay. So we have our normal force and gravity, but now that we know that gravity is the force we're breaking up into components, my question to you is, I'm not sure if maybe you didn't understand what my question was, but I'm
Mm.
sort of trying to ask, how would I split up this gravity force into two different components?
You'd have velocity, and then I don't know the other.
Okay. So velocity is not a force. Um, Velocity is really just motion. It's the speed of an object. So we can't really split it up into velocity. And I maybe I didn't entirely explain this, but when we split up forces into components, we're not splitting it up into like a different entire force. It's a component of a force. So it is still gravity, right? It's still going to be gravity. It's just smaller than gravity. Why? Because these two components together will add up to equal gravity. But we're splitting them up to match sort of this angle and sort of allow us to create this equation. So both the forces are still going to be gravity when you split them up, but they're going to equal slightly different values. So someone else can, I'll ask one more person, otherwise I will solve this myself. But
Would one be like parallel to the normal force
yes,
Yeah.
pointing toward gravity, and then one would be at 90?
yes,
So like
perpendicular 90
right
degrees.
angle, yeah, perpendicular to normal force.
Yep. So this is how we would split it up. Right. So as you said, one is pointed directly down in the normal force plane, and the other one is perpendicular. So very good. You're able to understand that. But I would say I think some of you guys are confused. So if anyone does have any questions about these inclined plane components, free body diagrams, let me know right now. But anyway, if no one does, I'm gonna sort of explain a few more things about this, and then we can sort of move off free body diagrams, get into more applications of Newton's laws, and sort of keep this class rolling. But if anyone does have questions, because I did realize a few of you guys may not have understood based on the way you answer the questions, just let me know, and I'm happy to go over it again. Yes, Sarvesh, you raise your hand. You haven't unmuted. Do you not have a question, or are you like raising your hand to tell me something?
Oh, I have a question. So,
Yeah.
do they have to be dashed lines, or
Okay.
can we do a solid line?
So again, in your free body diagrams, you do not actually draw out your components. They are
No, I
there
mean, like,
just,
should it be a dashed line? Like you draw a dashed line.
so again, we do not draw them out. We do not actually draw these dash lines. We don't draw them out at all on our free body diagrams. These are just there for the purposes of sort of understanding how do I create my equations and which quantities do I equate to each other? Because obviously these two components are going to be of different values. So I need to figure out Fn equals what, right? To sort of create that equality, that equation. And to do that, I need to know what is this quantity. And I can only do that by really drawing it out and figuring it out. But again, when I actually have my free body diagram and say it's this scenario right here, this is all my free body diagram would look like. Make sure obviously you're going to label your forces. this is what my free body diagram looks like. These components, they don't matter in the terms of the free body diagram. We only use them to sort of create these and set up these equations that we're going to use to solve for different variables. Yeah. Okay. Any more questions about this? Okay. I don't think I've received any other questions. If you do have any more, just feel free to let me know. We can go over it later if we have time. But I think one other thing I want to cover in this is sort of why is this component of the normal force? Why is it pointing why is it pointing left and down, right? Obviously it's supposed to be perpendicular, but why is it pointing left and down and not right and up, right? And a few guys might be confused about this. As I did this here, I pointed it in this direction, but it's really because we're pointing it in the direction of motion, right? We determine these components based on the direction of motion. So the reason I say that is because if we had a scenario where sort of the plane, I see you raise your hand. I'll get to your question in just a second. Hold on, let me just erase this so you guys have some more room. See this. Let me just sort of try that. So again, as I said, it's in the direction of motion. Why? So for example, good way to visualize this is using a different direction of motion. So we have this, right? But instead, it's sort of going upward. But for it to go upward, it either needs a starting velocity or it needs some kind of, we'll call it a force that's pushing it upwards at a constant velocity, right? So really, again, we're going to just draw our free body in the same way we always have, right? We have this N, we have this mg. But now we also have this other force, right? We have this other force, FF, that acts in a plane sort of perpendicular. So it's going to be like this, kind of not perpendicular to the plane. Sorry, parallel to the plane, perpendicular to the normal force, right? It creates sort of a 90-degree angle with this normal force. And when we draw our components, we'll get into more being able to cancel out certain things, trying to figure out when forces equal 0. But the idea is that we're going to sort of change up the directions of our forces based on the direction of motion. You said no. Do you not have a question, or did you raise your hand? Like,
Somebody asked a question in the chat, so I said no.
oh, okay. Did you? Okay, all right.
Can I
So
still ask a question?
so did you have any questions by raising your hand, or
Yeah,
you
I have a
good?
question.
Yeah. Go ahead.
So the reason you do it left and down is because it's in the same way that gravity is going instead of up.
Yeah.
Okay.
Mhm. It just seems like pretty easy to understand. Usually, gravity is a force that really pulls an object down to the earth, right? It's going to be always dragging you down. So usually, gravity directs a motion downward or towards a larger surface because that's the nature of gravity. It's an attractive force. So really that's why, because it's always going to be acting on the force in like a downward way or directing it to a different way. Usually, I mean, if it doesn't actually have a surface and say we're in space, it's going to be different. It's going to be pulling it towards some kind of planet or larger object. But we'll get into that entirely later. You don't need to worry about that for now. But really, gravity is really pulling an object down. So that's why we have these components pointing downward and not like upward and upward like that way. But do we have any other questions about this inclined plane free bodies? And if we don't, I'm going to get into Newton's laws right about now. Okay, I'll take that as we have no questions.
I wasn't
Oh.
here for the first two classes, so did we learn about anything else that's not like this?
First class, I kept it at basic math. Some of it was a little advanced, so that's why I scaled it back a little bit. But we just talked about graphing techniques. basic things that not actually physics, but that you will use, for example, in your
Yeah, I
problems review
watched the
labs.
videos that you posted.
Okay, yeah. So other than that, I think you should be fine if you were able to understand. Did you have any questions about anything I taught in the videos, or are you good with that?
No.
Okay, yeah, you should be good then. Saves time, yeah. Okay. So now, as we said, we have these Newton's laws, inertia. We have F equals ma, and every object has an equal, every action has an equal and opposite reaction. Okay, so these are our three big Newton's laws that we're going to use in physics. But so now that we know what they are, we need to sort of understand how are we going to use them in a real life scenario, a real life equation. I think the most basic one that I can start you guys off with is simply F equals ma. And it's as easy as it looks. Sort of as you take more physics, you will sort of get more problems where you have to use M and A to solve for certain variables, and really use this equation F, substitute other equations from your free bodies, and the way I say that is, for example, we have this equation Fn equals mg. I'll throw in a cosine theta just for the sake of components. You guys can ignore this for now. Many of you guys don't know what this is. But this is really another way of saying this is what our net force is, right? So if MA equals Fn, which equals mg cosine theta, we can really, in more advanced problems, you will sort of understand how to plug in one of these two values into F, right? Because they're all equal, which will create sort of inequality. But I'll get into those a little later. You have a question, Ishan. What is it?
Yeah, so Fn is normal force, m is mass. What would g be?
Okay, good question. So if you think of your force always in MA, of course, Fn, it's not a defined quantity. It's just labeled as normal force, and that's because we were already equating it to mg cosine theta. So that's another way to look at it. But if we always look at a force in the terms of MA, at least for when we're given it in this kind of value. So we have M, right? So we can just say, so therefore that tells us A. A is g cosine theta in this scenario. And if you just want to know what G is really the acceleration, right? It's the acceleration due to gravity. And it has a value. I can show you guys this value right now. You guys don't need to know it right now. But it's 9.8, right? This is our value. Another way to look at it, meters per second squared, because that is the unit of acceleration. But G is the acceleration due to gravity. That's the best way to think about it. And sometimes, even though this value is 9.8, sometimes problems will tell you it's 10, and they want you to use 10 instead. And that makes your calculations a whole lot easier because you don't have to worry about these decimals, and multiplying by 10 is a whole lot easier than multiplying by 9.8. But you're gonna have a calculator.
Another question.
Yep, what's up?
So in this case, what would theta be? Like, what would angle
Okay.
theta be?
Well, I don't have a defined value. This is just symbolic, but really the only way, the reason I have theta, for example, we can use our inclined plane, right? So we have our forces, right? But as I said, we need to break them up into components, right? So really, our components, right? For if you want to know, many of you guys don't know trig, that's why I didn't actually give you the quantities. But this is in this inclined plane specifically, this is how we would break them up into components. So we use trig, right? As I said, that's why I didn't get into it. Many of you guys don't know trig. But this is how we break up something into different components, right? We use trig. We use cosine theta and sine theta based on the plane and based on the angle, right? If this is theta, This is mg cosine theta. This is mg sine theta. So I just use this. It's just symbolic, so you don't actually need to worry about it. But that's where this theta comes in play. And theta is based on this angle right here. But we get this mg cosine theta, mg sine theta by breaking up our mg into different components. And if you guys do understand trig, this is how we would do it. And we can get into that a little bit later, like later on in the course. But for now, I want to stick to the basics because a lot of you guys don't know trig. But this is the best way to look at it. This is where mg cosine theta is coming from. So is that clear for you?
Yeah, thanks.
For sure. So anyway, if this is our equation, right? Right, as I said, we can plug in mg cosine theta equals ma and sort of solve for different variables, but we'll get into that later. For now, I just want to be able for you get you guys to understand the basic applications of f equals ma given certain quantities and values. So f equals ma. So I'm going to say an object has mass 100 kilograms. And it has an acceleration of 2 meters per second squared. It's constant to the right, so it's positive, right? And if you guys didn't know, the direction of motion in physics, typically, this is our standard direction. Right is positive and left is negative. Going to the right is positive and going to the left is negative. You can directly control this in your problems by sort of indicating which direction of motion you want to use. But this is our standard direction of motion. Yes, you have another question, Yushan?
Yes, sorry.
Yeah, it's all good.
Why is it s squared? Why would it be
Oh,
2 meters per
okay.
second squared?
So that's just the unit, but that is our unit of acceleration. So you guys don't know I would assume you guys don't know calculus yet, so I can't really explain the derivation of the unit. But really, if we consider position or distance, that's meters, right? This is our unit. I'm just talking units. Our velocity would be meters per second. And acceleration is just meters per second squared. So you see this like this pattern. So another way to look at this is meters per second to the 0, which is just meters over 1, which is meters. That might be a little confusing, but it's sort of you can see this sort of pattern from distance to velocity to acceleration. So I guess that's a way to look at it. And then you'll sort of understand that progression as you take more advanced math courses as well in the future. But meters per second squared, that's just the standard unit of acceleration. What's the thing next to the s in the Fn equation? I would assume you're talking about these little exponents.
No, in the Fn equation.
You mean the cosine? Okay, the next to the cosine. So this is theta. If you guys don't know, theta is the standard representation of an angle. So you may not understand when I just say theta, but it's really the angle. It's the value that I can plug in. I can say cosine of blank gives me a certain value, right? But it's just an angle. For example, it would be in this scenario, if this was our plane and this was theta, it would have a quantifiable value, and I could just plug that in there. Okay, so let's, as I said, mass of 100 kilograms, acceleration of 2 meters per second squared. The force would simply be 200. And we went over this in class 1, but you guys may not know this right now. But I want to see if anyone does remember. What is the unit? What unit do we use for force? So it's 200 what? Does anyone know? If no one does, that's entirely fine. We'll sort of learn this over time.
Is it a force per pounds?
That is not our unit. It's a good guess, but
Is it newtons?
newtons. There you go. You're good. Newtons. And you might understand, how do we get from kg m over second squared to newton? Well, it's not actually math we have to do. As you said, when we talk about force, we can just simply understand the basic unit of force is newtons. But to understand that, it is a known fact that newtons derived is just simply equal to kg. It's just simply equal to this. If you were to multiply kilograms by meters over second squared, this is the derived quantity of force. Never answer a question in this unit if you given kgm mass meters over second squared, even if it's not directly asking for force and just ask you to solve this equation, you will know that this quantity equals force. But they'll typically tell you just find the force given 100 kilograms, 2 meters per second squared. And you'll just know that the basic unit of force is newtons. Does anyone have any questions about that? I can show you guys a
I
few
have
more.
a question.
Yep, go ahead.
What's the difference between velocity and acceleration?
Good question. Explaining it in calculus terms, I'll just say that acceleration is a derivative of velocity. You guys probably do not know what that means at all, but velocity, the best way to think about velocity is the speed at which an object travels with, right? So if an object, it has a velocity of 2 meters per second, that means it is traveling forward. For every second it travels, it travels an additional 2 meters, right? That's what velocity is. Acceleration is the rate of change of the velocity. So if it has an acceleration, if say an object, right? Let me erase and give you guys a little extra space up here. If an object has an acceleration of 2 meters per second squared, and it has an initial velocity of 2 meters per second, that means for every second it travels, the velocity increases by 2 meters per second. Best way to visualize this is we have a block. So it initially travels at 2 meters per second. After 1 second, it's going to be traveling at 4 meters per second. And after another second, it's going to be traveling at 6 meters per second. So the best way to look at this is really acceleration is the rate of change of the velocity. Did you understand that, or would you like me to explain it in a different way?
Yeah, I got it.
Any further questions about that problem? I'll give you guys a little more advanced one right after for F equals ma. We get it? Okay. Any other? I don't see any other questions. So here's what I'm gonna do. A 200 Newton force is exerted on an object, right? Its mass is 20 kilograms. And again, this should be very easy for you guys, but using F equals ma, find the object's acceleration. So now we're not finding force, we're finding acceleration. And oftentimes it'll tell you to do something like this, find one of the other variables. So it's important to understand how do we do this. So can someone tell me, using F equals ma, how do I find acceleration? Yishan, you've been raising your hand a lot, so if someone else can raise their hand so I'll get a little extra participation from other people. If not, I'll call on you. But I want some other
You
people
repeat
to.
the question.
Find acceleration if this is force and this is mass. That's your question. So someone else who hasn't, I want someone who hasn't shared at all today, who hasn't raised their hand, asked a question, answered a question. And then
Oh, I was gonna.
no, you answered a few questions right earlier, so I want
I
someone
did.
who hasn't. I want to see sort of where other people are at as well. Shiva Harish, go ahead.
So you want me to solve what A is?
Yeah, find it.
A is 10.
A is 10. So how did you get that?
Well, 20 times 10 is 200.
Okay. Yep. That is a good way to look at it. But when we get more complex problems where it's not simply 20 times 10, I'm pretty sure this is what you did, but 20 times 10 is 200. But A equals F over M, right? This is another way to just look at F equals ma. It's the same equation, same law. But oftentimes we'll ask to find acceleration, mass, and if we need to find acceleration, we can simply set up the equation this way. And as you said, 20 times 10 is 200, or 10 is equal to 200 over 20. It's a very simple problem,
Okay.
but it's just important that you guys understand how can we take F equals ma and manipulate it and find other variables other than just force. So does everyone understand? I don't want to erase it yet. Does everyone understand this basic F equals ma? Or do we have any outstanding questions that I have not gotten to? Anything at all? Just let me know. Got a thumbs up. Okay. We got no other questions about this. Okay. I guess now we can talk about some of our other laws. We can talk about inertia. It is an important concept to understand, but typically you'll be getting questions like this in sort of a conceptual manner. I'm gonna say conceptual. We're sort of ignoring the numbers and we're just sort of understanding how can I apply this law to my problems, right? So as I said, in inertia, an object stays at rest or remains in motion until acted upon by an outside force. And say we have an object traveling at a constant velocity. And as we went over, velocity and acceleration are different. So it's traveling in this direction at a constant velocity. So it is in motion. And it will not move at all. It will not change direction or change speed unless an external net force is going to act on this object, right? So I'm gonna quickly say I add friction. So can someone tell me what will happen over time when I add this force? What will change about this object's motion? Like, will it slow down? Will it stop? Will it keep going at the same speed? Yeah, Vishnu, let me know.
Slow down until it stops.
Yep, there you go. As we add this friction force, it'll slowly slow down as it slides. Sort of this velocity will sort of decrease and then it'll eventually stop. And now if let's introduce a force of the same magnitude as the frictional force. It means they're equal, but they're just in opposite directions. We'll call this force F. So someone is pushing on this force to counteract the friction force. What will happen to this object's motion as it continues to travel? Someone can raise their hand and let me know. Will it keep going at the same speed? Will it speed up? Will it slow down?
I have a question for this. So if someone is pushing it, does that mean they're going to push it once and let it go, or they're going to continue pushing it the entire time?
Good question. But in physics, when it says someone pushes on an object, someone applies a force, it's usually a constant force that's going to continue to be applied until it specifically indicates that it won't be applied anymore. The only exception to this is when it specifically tells you someone pushes an object like off a cliff or like pushes an object or launches an object, right? With some kind of mechanism. But usually when there's an applied force F, like on a surface or on an incline, that person continues applying that force until
So
it moves.
wouldn't the object be at a constant rate the entire time?
Yep.
Assuming that they don't stop.
So that's exactly what I wanted to ask you guys. Because the frictional force and this force are equal in magnitude, it continues to travel at the same velocity because even though there are external forces, these two cancel out and there is no net external force. So that determines inertia. So say I made this a little bit bigger. So we'll draw it out that way. To a point where now F is greater than FF. Now what happens to this object's motion? Does it speed up? Does it continue at the same rate? What's gonna happen?
It'll speed up and continue with a faster rate.
Okay. So it will not, it will speed up, right? There you go. So it now, because F is greater than FF, we have an external force, a net external force again. But instead of like compared to our first example where it was pointing in the direction opposite of the motion, which eventually caused it to stop, right? Because it's just entirely friction. But now we have a sort of a net force. So we'll say, well, this is usually the signal or the sign that indicates net. So you guys don't really need to know this yet, but when you see something like this, it sort of indicates net, right? That means the overall force, right? So it equals F minus FF, right? So I just want you guys to visualize this. So now that we have net F is positive, we can see that because it is an actual quantity and value, it has an acceleration. So we can use F equals ma. If this is a quantity, that means both of these have to be some kind of number, because any number times 0 is 0. So an object will have to have a mass, and if it has a force, it has to have some kind of acceleration in some direction. And that causes it to speed up, right? As we said, it's the rate of change of velocity. So if there's an acceleration, this velocity will continue to increase and it'll speed up. I believe you said it will continue at like a higher rate. So I'm not sure if this is what you meant, but it'll continue to speed up forever until another force acts on it, but it will not continue at a specific higher rate. So it'll just continue to speed up over time. So yeah, so conceptually, when you see that there is a net force, you have to always remember, if there's a net force, there is some kind of acceleration, and that's why the object changes motion, changes speed, etc.
Wait, is this because since the regular applied force, I mean the applied force is greater than the friction, it would always get faster instead of being going fast and then slow and then staying constant?
Because the applied force is greater than friction for the entirety of its motion, right? That's what we assume in these problems. If a problem, right, told you that this applied force is initially greater, and that causes a specific acceleration, but over time, the applied force reduces to the magnitude of the friction. In that scenario, what you would do is understand how fast it accelerates at the beginning, but then also realize that towards the end, sorry, not towards the end, but when it tells you that the forces are equal, that there is no more acceleration, and now it's continuing at that higher rate.
I have one more question.
Yeah.
Sorry.
Go ahead.
So in what you just said, like if it increases and then like the applied force and then it becomes the same as the friction. So then wouldn't it make like it would become faster, and then when it starts becoming the same force as the friction, it would slow down and become a constant rate?
So it will not slow down, right? Even though the force reduces.
Oh wait,
All
yeah, it will still speed up, but except it will speed up less.
No, I'm not sure if maybe you're not wording this correctly, because you don't know this entirely, which is probably new to you. But conceptually, this is how you're going to understand it, right? This is the best way to understand this problem. So it will not speed up, it will not slow down. So once these forces become equal again, right? Once F and FF are equal, that means we have no more change in the velocity. No, because why? Because there's no net force, and that means there's no acceleration. So it will not speed up or slow down or reduce in any way. All that changes is really the acceleration. So as we said, say we have an object that has an acceleration of 2 meters per second squared, and it has an initial velocity of 2 meters per second, right? This is our initial velocity. So after 1 second, it becomes 4, right? And after another second, it becomes 6, right? But now what happens is we don't have the acceleration anymore. The acceleration disappears, and that's because this net force is 0 again. And again, that means F is equal to FF. So really, this object will just continue to travel at 6 meters per second. When these forces are equal, there's no acceleration, but that does not impact the velocity or like cause it to reduce. So when there's no force, it doesn't like reduce the velocity or it doesn't increase the velocity. But
Okay, I get it. So
yeah,
it's like, so for the problem before, it would increase forever, slowly,
yes,
but this
yes,
time when it stops, it'll stay wherever it increased until.
yep.
Okay,
There you go. You're understanding now.
thank you.
So force doesn't directly impact velocity. In these scenarios, the best way to look at it is force is going to impact our acceleration, and that acceleration we use to determine how our velocity is changing. But it's important that we make this equation and sort of use F equals ma, so we know how our velocity is changing. Because we do not want to just go straight from our force and say, oh, I know this is conceptual, but when we actually use our numbers, we don't want to just go straight from force to velocity. It's not a good conversion because there's no direct equation that's going to link these two in a basic scenario like this. So it's important to sort of use force and equate it to ma, and then sort of we can see, oh, it accelerates this fast, and that's how our velocity is going to change. So does anyone have any more questions about inertia, or we can get into the final of our Newton's laws? In the chat. What is
I
the
have
formula
one
of
question.
okay, so you ask yours and then Arav, I'll answer yours right after. Ishan,
Me?
you can go. Yeah, you can go.
Okay. I didn't completely understand what that symbol was.
Which symbol? Just let me know.
Next. Yeah,
Like,
like
oh,
they're
this one
the
right here?
first.
This one?
Yeah,
Okay.
yeah, that one.
So good question. As I said, that is a force that indicates net. That means our total quantity. So because we have two forces acting in a different direction, right? F and FF, right? So that means there has to be some kind of net because they're not equal. So we can't say FF is equal to F. In this scenario where we said F is greater than FF, that means when you subtract the two, there is still some value, right? There's still some net force. And this is what that symbol indicates. It just indicates sort of a sum or subtraction between the two. It's like a composite or a combined amount.
So when you subtract it,
You muted.
so when you subtract the two, that force is always going to stay the same. Like the value that you get is the force that's going to stay.
Yes. Okay. I think I sort of understand what you're trying to say. When you subtract F and F, that's our net force, right? So as you said, that's the force that's going to remain. So that's the force that's actually going to act on the object. That's going to change the direction of motion. Because if we have two forces that are equal, even though those forces both do their own work or on the object, those will eventually cancel out because they're equal in magnitude, right? So they won't actually change the direction of motion or impact the object's motion in any way. But when we do have this net force, right, as the symbol indicates, because F is greater than FF, is that sort of begins to cause changes in motion of the object and such. Arav, you say, what is the formula of inertia? Well, inertia doesn't have a formula. It's just sort of a conceptual understanding, right? So Newton's laws don't all have formulas. F equals ma is the only one that has a specific formula. The other ones are more conceptual, but as I said, inertia is an object stays in motion or remains at rest at that same speed, right? So when it stays in motion, it's going at the same speed until acted upon by an external net force of some quantity. So we can just use this idea to create these really F equals ma equations, and that those will allow us to determine, do we have a net external force, do we have acceleration, and therefore an object's motion will change in some way. So there's no direct formula. It's just sort of this understanding that an object stays in motion or remains at rest until acted upon by an external force. And you can use that same understanding. If we see an object changes in speed, for example, from 20 to 40, right? We know, therefore, there means there must be some external force that's acting on the object, some net force that changes the motion of the object, right? Because it's not remaining at that same constant velocity. Any more questions about this because we don't have too long, and I just want to quickly get into the last law a little bit more. Guys, a couple minutes. Okay. I don't see any other questions. So quickly, our last law that we need to talk about is the one you guys have heard probably a bunch of times before. Every action has an equal and opposite reaction. So this is our keywords right here. Equal and opposite reaction. So we need to understand what that means. So this is the example I used when I first explained this last class. We have a small box and a big box. Now basic knowledge or basic like sort of common logic will sort of tell us that because this is bigger, if a force is exerted on these two that causes these two objects to exert a force on each other, this object will exert a greater force. Why? Because F equals ma and the mass is greater. But people, when they do this kind of calculation in their head, they forget to realize that we do not know acceleration in any way, right? We don't understand, we don't know, or we can't quantify acceleration. Because we're not given it. We're not given the velocities in these scenarios. So in some scenarios where you can't look at acceleration, we have to just always remember that if one object exerts a force on the other, this is going to exert the same force back, equal and opposite, even if this mass is 100 times greater. And it goes the same way. Because this is a larger object, it might exert a greater force on this initially. But so if this exerts a greater force than this exerted on this initially, this will simply exert the exact same force back. And are these equal and opposite pairs? It really helps us because one of the most common examples I've used is just an object on a flat incline. And we have this normal force and we have gravity, right? No, sorry, I drew these the wrong way. MGN. Really, in this scenario, these two are an equal and opposite pair. And when we have forces that are equal and opposite, they do not create an external force, right? And there's no change in motion, right? Now, it is also important to remember that not every force is counteracted by an equal and opposite one. There are certain pairs of forces that create this equal and opposite sort of reaction. That's one of the most common ones you're going to get is when you have a flat incline, N equals mg every time. But these internal forces between two objects, those are also going to be equal and opposite. And let me redraw this with another big object right here. So these two objects, I know it's not perfect drawing. It's not perfect drawing. But say they are entirely touching, right? And we have an external force F that pushes on this. And that will eventually cause really these objects to push. This will cause this object to push into this. And these forces are exerted, as I said, equal and opposite, right? These are what we call internal forces, right? These internal forces they tend to be equal and opposite. And therefore, they're not doing work on the system as a whole. This is the only force that does that. So this might be a little confusing, right? But not every force is equal and opposite. And though we say that every action is an equal and opposite reaction, this force is still a net external force, right? It is doing work on the system. And because of that, it causes these internal forces, right? And these internal forces are equal and opposite. But just remember that when two forces are equal and opposite to each other, they do not actually change an object's motion in any way. Those internal forces are generated by some external force, and that external force is doing work on the system. But these internal forces will remain equal and opposite. But for the sake of understanding Newton's third law, we can draw these internal forces out to sort of understand that these forces actually do not, the contact force between the two objects doesn't actually do work on the system. It's just equal and opposite. But this is the basic understanding of Newton's law, Newton's third law. And I think the most common mistake people make is that either they actually quantify these internal forces and say, oh, this actually does work on the system, or they just generalize every force is equal and opposite, and it's some kind of equal and opposite pair. That when this force is exerted, there will be a force, and in theory, right, because using Newton's third law, we can say that when I push a block, for example, right? So say I push a box, right? That box will still kind of exert a force back against me, right? So in theory, if we consider the system of, okay, let me just draw this out for you guys. I think this might be a little confusing, but let me just quickly draw this out. So say I'm pushing this box, right? Pretend I'm pushing this box, right? Because of Newton's law, we do have to understand that. So I exert a force. This object will exert a force back against me, right? That is equal and opposite. But the thing we have to understand is that typically this person right here, they aren't actually in the system. We only consider the system of the object or the box itself. And that allows us to classify F as an external force and not sort of an equal and opposite pair that doesn't do any work on the system. If we consider the system of the box and the person, now we have to say that this force is an external and it's just simply an internal force, and it doesn't actually do any work. So while every action does have an equal and opposite reaction, when we consider external forces, those actually do work, and we can't actually say that there is a force that counteracts an external force because it's out of our system. So that might be a little confusing for you guys to understand. So do you guys have any questions? I can maybe explain this a little easier for you guys, but it is a little complicated because we have to consider what is and what's not in our system a little bit. We don't have too much time, so if anyone has any questions, please let me know right now about this, and if not, I'll post some videos as well. But I do understand that right here, this can be difficult. For understanding what's in the system. What's that? Yeah, go ahead.
So the force the man is pushing is
Yeah.
part of the thing, but the man itself not.
Yes.
Okay.
So the person pushing exerts this external force F, right? So it is from outside the system, and that's why it's external, right? That's what's an external force that exerts on the block. But we cannot count this person in if we want to classify this as external. So if the person's in the system, it's no longer external. It's an internal force, right?
I
And that,
understand this, but it's 101. I don't know if we should go to calculus yet, but
yeah, if you don't have any further questions, you are welcome to leave. I'm just trying to stay here, just to answer a few more questions if you guys
thank you.
have any.
Bye.
Good.
See you on Friday, I
Yep.
think.
Next class is on Friday. If anyone has any questions, just let me know. Otherwise, I will end this meeting.